Hey my lovely level 3s, and welcome back to 3.4 Atomic Structure and Bonding. We're up to lesson 10 on polarity, which is exciting. We're halfway through the external. So this is to describe the polarity of the shapes that we've been doing with 5 or 6 electron density regions. So there's a wee starter task that I'd love you to have a guess using your knowledge from level 2, whether these would be polar or non-polar. So please just pause, write down what you think, and I'm about to justify it. Hopefully this lesson is quite straightforward for most of you because it's pretty much exactly the same as level 2 but with the new shapes. Okay, so this shape here has 6 electron density regions and all of them are bonding. Which means it takes on the shape of octahedral. So I'm not going to go through justifying the shape right now. This shape here has got 5 electron density regions, 4 of them are bonding and 1 is non-bonding. So this is a seesaw. Okay, so what we're going to do is we're actually going to go through whether these are polar or non-polar. Now, this shape here, because it's a parent geometry and symmetrical, and all of the atoms surrounding are the same. This shape is symmetrical. Because this shape has a lone pair, we say that it is not symmetrical. So that's the same rules as last year. Okay, so anything with a lone pair is not symmetrical. You will learn this year that there are 2 exceptions to that, but anything with a lone pair is not symmetrical, and then any of your parent geometries are described as being symmetrical. So let's go through this answer. So in SF6 there are 6 times SF polar bonds, and the reason why those bonds are polar is because F is more electronegative than S. Okay, so there are 6 SF polar bonds because F is more electronegative than S, and we know why. We would then say that the octahedral shape is symmetrical, so the dipoles that are created cancel, and this shape is non-polar. Hopefully you're like, oh my gosh, I remember all this stuff. So now let's jump onto this shape here. So in SF4, there are 4 times SF polar bonds, okay, and that's because F is more electronegative than S. Okay, now due to this lone pair, this shape is not symmetrical, therefore the dipoles cannot cancel, and this structure is polar. So I hope that makes sense, and we're going to be learning about this during this lesson. Just a wee reminder, this is from earlier in the topic. Electronegativity increases across the period and decreases down the group. Okay, and 2 different atoms in a bond create a polar bond, and that's because there's an electronegativity difference, which means one of those atoms pulls those electrons, those bonded electrons, slightly more. So which are polar and which are non-polar if all of the surrounding atoms are the same? So all of your parent geometries are described as being symmetrical, and therefore they will always be non-polar if the surrounding atoms are the same. So therefore linear is one of our parent geometries, so it is symmetrical and it'll be non-polar. Trigonal planar is a parent geometry, so it's symmetrical, it'll be non-polar. Okay, trigonal bipyramid down here, I think the bottom's a little bit cut off, I apologize, a little bit of the F. So trigonal bipyramid, that's symmetrical and it'll be non-polar. And octahedral down the bottom here is symmetrical and therefore it will also be non-polar. I'm just going to try and... oh no, it's not going to let me drag that bigger. And it will be non-polar. So anything that has that is a parent geometry is classed as being symmetrical. Okay. So moving on from there, let's just have a wee summary. So this slide's the most important. I try not to do too many like words and stuff because it's all quite straightforward. So if all of the atoms around the central atom are the same, then your non-polar shapes that are symmetrical are all your parent geometries. So linear, trigonal planar, tetrahedral, trigonal bipyramid, and octahedral. There are two exceptions, and I'll come back to those in a second. Now, all of your shapes, which will always be polar, and that's because they're not symmetrical, and there's nothing that'll ever change with this. So because there are lone pairs, these are not symmetrical, always, is bent, trigonal pyramid, seesaw, T-shaped, and square pyramid. Now, hopefully what you're thinking is, well, hang on a second, Miss Sutton, two of the shapes you've put in the non-polar symmetrical column have lone pairs, and that's correct. So one of the shapes that is an exception to the rule is if this was your trigonal bipyramid shape, so 1 up, 1 down, and 3 in the middle, if we take away the 3 in the middle plane and just have the one above and below, the axial plane, this is linear, and this is the one time where there's two times, one of two times where there are lone pairs, but the shape is still symmetrical and non-polar. So that's linear with 5 electron density regions. Okay, so that one's also non-polar. And the other example is that square planar. Okay, and the reason why is because the axial plane has completely gone, and so they cancel each other out. So this is a planar shape here. So if all of these atoms, these bamboo sticks, are identical, then this will also be non-polar, even though it's got lone pairs. So the two exceptions are square planar and linear with 5 electron density regions. So yes, they have lone pairs, but due to their shape, they're still symmetrical and non-polar. Whereas though anything that's got lone pairs normally is polar and they're not symmetrical. So if you can remember this slide, this is the big one, and we're going to do some examples. So let's describe the polarity. So one's a level 2 shape and one's a level 3 shape. So first of all, we're not going to justify the shapes right now, but we've got 1, 2, 3, 4 electron density regions, okay, and this shape is trigonal pyramid because there are 3 bonding and 1 non-bonding, so that's trigonal pyramid. Okay, so let's justify its polarity. So straight away we can see there's a lone pair, it's not linear or square planar, so we know that in the end this is going to be polar. So you can know that going in, and so now we need to justify it. So we're going to say that there are 3 times PCl polar bonds, and these bonds are polar because Cl is more electronegative than P. Okay, so there are 3 PCl polar bonds because Cl is more electronegative than P. Trigonal pyramid is not symmetrical, okay? And so what that means is that the dipoles will not cancel. So dipoles do not cancel, and the structure is polar. And I hope that makes sense. Okay, so the dipole here and here and here can't cancel out, and so we end up with a net polarity. So one side of that molecule, if we look here, that'd be delta negative, delta positive, delta negative, delta positive, delta positive, delta negative. What you end up seeing is that this side of the molecule is negative and this side is positive, so it has a net polarity to it, and that's what we mean by polar. So let's look at the example of PCl5. There's 1, 2, 3, 4, 5 electron density regions and all are bonding. So this is trigonal bipyramid. And this is apparent geometry and all of the surrounding atoms are the same. So we're like, oop, it is going to be symmetrical and non-polar, and we know that going in. So let's describe the shape. There are 5 PCl polar bonds. And why they're polar is because Cl is more electronegative than P. It is symmetrical, okay, which means that the dipoles will cancel and the structure is non-polar. So I hope that makes sense, and let's just have a look. So that'll be slightly negative, slightly positive, slightly positive, slightly negative, slightly negative, slightly positive, slightly negative, slightly positive, slightly negative, slightly positive. And what you can see is there's not one side of this that's positive and negative. All the surrounding atoms are negative and the inner atom is positive, which means there's no net dipole. Those dipoles are cancelling each other out. So I've typed this up for you of those two answers so you could have a look through. Feel please feel free to pause and read them properly, or they're on your OneNote. So now that we've been through if all the surrounding atoms are the same, then let's just recap. We'll go back a couple of slides. So if all the surrounding atoms are identical, then that means all of your parent geometries, so linear, trigonal planar, tetrahedral, trigonal bipyramid, and octahedral, are going to be symmetrical and non-polar. There are 2 additional ones with lone pairs, which are square planar and linear with 5 electron density regions, and it's because they are also symmetrical. All of your shapes with lone pairs otherwise are not symmetrical and polar, and so they are bent, trigonal pyramid, seesaw, T-shaped, and square pyramid. Okay, so what happens if the atoms surrounding are not identical? So I'm actually focusing on this section here for now. Now, we don't do vectors in NCA level 3. However, they can be quite useful to describe what's going on. So you can see here that in this example of trigonal planar, you've got X, X, and X. So the surrounding atoms are identical, which means that this shape is symmetrical and the dipoles cancel and it is non-polar. However, in this bottom example, you can see you've got 2 X's and a Y. So even though this shape is symmetrical, because the dipole strengths are not identical anymore, they cannot cancel, and this will be polar. Okay, so you do need to be able to justify that, and so I've got an example here. Okay, so the example that I'll show you, I actually should have put a slide so I could draw it, is CH3Cl. So this is just a tetrahedral shape, but it could be anything. So if we draw this, it looks like this, the Lewis structure I'm doing. So you have H, 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 and then Cl. Okay, so that's the Lewis structure. So it's tetrahedral, so it's drawn straight, straight, then solid, and dotty. And so you've got H, 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 and Cl. Now here we can see that there are 3 CH polar bonds. Okay, and that's because C is more electronegative, and there's 1 times ClC polar bond, and that's because Cl is more electronegative. Now, despite the symmetrical shape of tetrahedral, due to the difference in electronegativities between these, the dipoles cannot cancel, and this structure would be polar, and that's how we describe it. So I've typed that out for you here. So this is me justifying the shape. So it's tetrahedral. I'm going to jump from here. So there are 3 CH polar bonds, as C is more electronegative than H. There's 1 CCl polar bond, as Cl is more electronegative than C. Despite the symmetrical shape, the dipoles do not cancel due to the difference in electronegativity of the surrounding atoms, and therefore the structure is polar. So I hope that makes sense. If you have any questions, please let me know on Teams. Okay, I'm going to be back in a second to do the second part of this video.